curves are the true curves that matter particles follow. So one should really derive this from the action principle. And this helps in a sense to have a consistent theory. So if you write down a modified gravity theory and you just say my energy momentum tensor is conserved, then you might break something. You might break something without realizing that you've broken something. And I'll show you what this looks like in a very specific setting in a moment. So everything I do will start from an action principle. So I'm showing you here the usual Einstein-Hilbert action, where, as I mentioned here, you have this term that is linear and curvature, and over here you have a meta-Lagrangian. I'll talk about this meta-Lagrangian in a moment, because the moment I write something like this down, I'm actually making various assumptions that I'll discuss. So as always, ask the Ricci scalar. This here is our volume element. I have coupling constants and matter fields psi. The interesting thing about this meta-Lagrangian is that the moment I write this very specific meta-Lagrangian that I did write, I am actually assuming already a minimal coupling procedure, because what I'm saying is that my meta-Lagrangian depends on the metric, some matter fields, and covariant derivatives of matter fields. However, this does not include various non-minimal couplings. So non-minimal couplings are couplings where the matter fields couple to some geometrical quantities. So the Brown-Sticky term is sort of one of the most well-known ones. We suggested something very similar. And then if you recall the talk of Francisco Lobo, he mentioned this book that he had written with Tiberio Harco. And they have written an entire book on, in a sense, non-minimal couplings. So there is a lot that can be done with non-minimal couplings. And they're very different from our minimal couplings. So hence I distinguish them. And what is interesting about these non-minimal couplings is that they're in a sense very hard to constrain using observations. And why do I mention these? Well, you will see this in a moment. So some of these coupling terms that are introduced are topologically motivated. So an idea that goes back a good few years is where someone suggested, well, let's have a look at the Gauss-Bonnet term. If you take the Einstein-Hilbert action and you add the Gauss-Bonnet term to this and you vary with respect to the metric, you do not get any field equations that differ from the Einstein field equations. And that has to do with the fact that the Gauss-Bonnet term is in fact also a boundary term, and boundary terms don't contribute to equations of motion. You have to be slightly careful with the statement because you could have a manifold with boundaries. But other than that, you can more or less say boundary terms don't contribute to equations of motions. However, if you put a field in front of this boundary term, then it's no longer a boundary term, because if you use integration by parts to integrate this term out, the integration or the derivative in this term sort of maps on the field and it doesn't disappear. So if you couple anything to a boundary term, then you get contributions. Likewise, if you have a boundary term that is not necessarily topological, so all my boundary terms will always be called B, then if you add any boundary term to the Einstein-Hilbert action, again, it doesn't contribute to the field equations, but if you then couple this boundary term to, say, a matter field, then you do get something. And the first message I want to give you is please make sure to remember boundary terms. They're actually really important, and they will explain a lot of the bulk of the talk. So first, so I said there are lots of gravity models out there. So in a recent contribution, which will eventually become a book, we tried to create some figures. So colleagues of mine did this, where we tried to link all these different theories. And what I want you to look at is sort of this kind of blob here. So all of these theories, I want you to just think about these so-called teleparallel or modified teleparallel theories. And teleparallel gravity, I'm just pointing this out, is equivalent to general relativity if it is formulated correctly. So there is an equivalent formulation of general relativity in a teleparallel setting. So all these theories are somehow naturally related. And then one can produce another figure, which was also done by my colleagues, which looks a bit like this. And they produce two different figures because it isn't quite clear from first principles how all these theories are related. And I now want you to, for instance, look in particular at f of r here. And what I'm able to do is I'm able to look at this black region in the first figure, and in particular f of r in the second figure, and I can explain exactly how these theories are related. And this is what I'm trying to do. So in order to do this consistently from a maths point of view, I'm starting with an Einstein-Hilbert-like action. So note my overbar here is the Ricci scalar, but it indicates that I'm taking into account various other geometries. So this is not the standard Levi-Civita Ricci scalar. It is the one with non-metricity and with torsion. And I can decompose this Ricci scalar. So many of you will have seen this term G. This term G is the term that sometimes appears in the Einstein action. This is the term that is just quadratic in the connection. And it differs from the standard Ricci scalar by just the boundary term, which I denote B. And it turns out that if you take the full Ricci scalar, you can decompose it into a Levi-Civita connection part and a boundary term, a torsional scalar part and another boundary term, a non-metricity scalar and another boundary term, and one cross term. And this cross term mixes the torsion parts and the non-metricity parts. But this is sort of quite remarkable. I think very few people have sort of written it down like this before we sort of spotted that actually for every geometrical scalar, there is an associated boundary term. And please note these boundary terms will be the really important ones. So this Ricci scalar, as I said, can be used in GR, and if you vary G with respect to the metric, you also get the Einstein field equation. So as I said, this is the so-called Einstein action. And then I'm mentioning here what the torsion scalar is, some non-metricity scalar and a cross term. But the most important thing is here, these guys, I can change to red. It lets me do. So all these guys here are boundary terms, and they will be very, very important for what I'm going to do. So again, I must mention very briefly these metric affine theories. So if I have some action that depends on a metric, possibly a tetrad field, torsion, non-metricity, and scalars, then what I do in order to derive the equations of motion, I vary with respect to all my dynamical variables, matter, non-metricity, torsion, tetrad if needed, and the metric tensor. So I only need a tetrad, strictly speaking, if I either work in the teleparallel equivalent of GR, if I want to couple fermions. Otherwise, I don't really need the tetrad. One should know that both these variations are related. So they're not independent because you can compute the metric from the tetrad. So the variations with respect to each other, they're also related. But that is a slight technicality. So let me jump straight into this. So I previously mentioned various of these modified theories of gravity. So in the early 2000s, F of R started. In 2007, F of T joined the scene. Then in 2015, we sort of explained the relationship between F of T and F of R. And then in 2017, people started with something that is called F of Q gravity. And then someone suggested working with the modified Einstein action in 2019. So that was Milgram, and he made relations to Mond. I will mention this. And the key result of what I'm going to tell you is really that these theories are not at all independent. So often when you open a random paper and look at some field equations in any of these three settings, then someone might well say, these equations are very similar to the same equations in the different setting. So in particular, here comes my spoiler or my teaser. If you write the field equations out, like we have done in this very specific way, then you are rather tempted to assume that, okay, this is not a coincidence. There must be an underlying reason why these equations actually look the same. And if you look here, all these field equations contain the Einstein tensor, and then plus or minus these funny scalars that appeared in my Ricci scalar. And what we are able to do, we can really explain why actually all these theories are in a certain sense equivalent and how they can all be related to each other. So the key equation for relating F of R gravity and F of T gravity is again our decomposition of the Ricci scalar. And in this framework, there's no non-metricity, that we can simply set Q to 0. If you set Q to 0, the BQ goes to 0, the C goes to 0, and actually you end up with a very simple equation, which just reads 0 equals R plus T minus TB. And this is a boundary term, which doesn't contribute to equations of motion if you have a linear action. And then you end up with this very well-known equation here, this one, which says that the Einstein-Hilbert action, which contains the Ricci scalar, can be written in an equivalent way using only a torsion scalar, in which case one speaks of the teleparallel equivalent of general relativity. So this is easy to see. But what happens when you put F's around these things? Well, there are a few things to note. So if you put an F around R and you think about F of R theory, then you have a fourth order theory. This means the field equations contain fourth derivatives. If you look at F of T gravity, you have second order field equations. However, both these theories reduce to general relativity if you assume that F is a linear function. So if you look at this, you might be tempted to say, okay, I don't understand how these theories are related, because it is difficult to relate a fourth order theory to a second order theory somehow. Unless you have a limit where some epsilon is in front of the highest derivatives, and then you send epsilon to 0. That is sort of is sometimes used in singular perturbation theory, but that is not actually what's going on here. The missing link is simply the boundary term again. The boundary term contains all the terms which actually contribute to the fourth order field equations in F of R. And if you trace this boundary term correctly, then actually you can understand how these two theories are related. And in a sense, what we said in 2015 was that the correct, in quotation marks, the correct theory to actually study is not F of T gravity, but it is F of T comma BT gravity. So you need to keep the boundary term inside your action. And if you do this, what you get is the following nice picture. So in the top left here, you have F of TB gravity. If you insist on a model that only contains second order field equations within this family, you have to go to F of T gravity. However, if you insist on a theory that is invariant under local Lorentz transformations, you are forced to go down and you end up with F of R gravity. And what you see is that these theories are sort of, they are related, but they're not related directly. You have to go this indirect path, and both correctly go back to GR. And this visualization for me explains a lot. So all the higher order equations are in the B term. However, if you insist on second order equations, you can leave out the term, but then you lose Lorentz invariance. So over here, the theory is second order, but not invariant under local Lorentz transformations. Down here, the theory is invariant under local Lorentz transformation, but fourth order. So you have to sort of pay a price for going either way. Both reduce to general relativity. And it is really this that motivated us to look at this again a few years later. So here again is my decomposition of the Ricci scalar that I mentioned before, and explicit expressions for the G and the B, and the Einstein action that I mentioned to you. So again, this gives the Einstein field equations. That is quite well known. If I now put an F around this, so I'm considering a model that is an arbitrary function of the scalar G and the scalar B, I get these field equations. I'm sorry, they are slightly complicated, but I just decided I stated them once. I won't be working much with them, but you see here, this very first line is the line I showed you earlier, because I assumed that there was no dependence on the B term. And this is here the Einstein tensor. You see it is an Einstein-like equation with an energy momentum tensor here on the right. And in this approach, that is the standard metric energy momentum tensor, because we varied with respect to the metric only. Okay, and I mentioned to you before, I'm giving you a little bit of notation here. This notation you need, if you look here, there is this E term. So someone might ask, what is the E? If I give you the answer, you might not be so happy, because the E contains an M. So this is the Schouten bracket, which is the thing that defines the Christoffel symbol in a sense. And that M here is the derivative of G with respect to gamma. So it is a slightly long object, but it is quite a it is a very natural object, this M. To show you it is natural, if you computed the Lie derivative of G and the Lie derivative of B, where you must now note that G and B are not true coordinate scalars, then you get the usual term plus a correction term. And this correction term, or the term that tells you it isn't really a scalar, contains this M again, which is unsurprising. And you see, if you compute the Lie derivative of G plus B, which is the Ricci scalar, then those two terms cancel and you get the correct behavior of a scalar. So what does this mean for the energy momentum conservation equation? I told you before, the only correct way to do this is to actually compute the Lie derivative of your total action, use those two expressions which I have given them, grind through this. Is a slightly lengthy calculation, but if you do this, you end up with this one line up to various boundary terms. And what you see here is, you see over here the covariant derivative of the energy momentum tensor, and you see on the left-hand side here some second partial derivative of this object M again. So it turns out this is a really not very well-known result. So this guy here actually vanishes in the limit of general relativity. And it is one way to write the Bianchi identities with partial derivatives. So this can be found, I think, in a paper by Möller in the 50s, but it's not a well-known result. And even if you try to prove by hand that this is really the Bianchi identity, you will sit there for a very, very long time because it is written in a most unnatural way. But this is in the limit of general relativity. This is indeed the Bianchi identity. So the interesting thing here is that for this general model, you see, you get some kind of conservation equation, but you can't immediately assume that the energy momentum tensor itself is conserved. It is this combination that is conserved. So not this on its own or that on its own. And this is in fact important for all modified theories of gravity to do this procedure. And as I said before, this is in a sense Noether's theorem for our model. And as before, so I told you f of r gravity has fourth order field equations. F of g has second order field equations for a very similar reason. And as before, all the fourth order contributions come from the boundary term. And as before, a linear function in G and B gives back general relativity. So I can create a picture similar to my previous picture. So you see this was the 2015 picture, this is the 2021 picture, which is pretty much a carbon copy, except that you change the arguments of the function. However, there's one interesting difference, and that is f of GB. If you insist on a diffeomorphism invariant theory, then you end up with f of r. So in 2015, you had to insist, because it was the teleparallel framework, you had a Lorentz invariant theory that gave you f of r. Here it is a diffeomorphism invariant theory that gives you f of r. And this observation sort of allows you to now think about how can you break either local Lorentz invariance or diffeomorphism invariance. In particular, I can also tell you how to combine the two pictures, which is quite nice, really. You simply write down an arbitrary function that depends on all those scalars that I've mentioned before. If you don't assume curvature vanishes, you are actually working with generalized metric affine theories. If you insist on curvature vanishing, you are in some kind of a teleparallel setting where the space is globally flat. And then if you assume that non-metricity vanishes, you end up with f of t gravity. Or if you assume that torsion vanishes, you end up with f of q gravity. And f of r gravity somehow could be added to this figure to a right-hand side, but I was interested in showing the relationship between these two theories. So how can we break invariance? So as I said, in f of r gravity, you can't really break much. The theory is invariant under local Lorentz transformation. It's invariant under diffeomorphisms. So actually, this theory is what it is. However, for the other theories, you can do quite a few things. So on f of g gravity, it is invariant under local Lorentz transformations because G is a Lorentz scalar, but G is not a coordinate scalar. And therefore, you can somehow break diffeomorphisms. In f of t gravity, so in teleparallel gravity, it is well known the theory is not invariant under local Lorentz transformations, but is invariant under diffeomorphisms. So here, you could break local Lorentz transformations. And likewise in f of q, it's also the diffeomorphisms you can break. So let me show you how you can break this. And this is actually a very, very elegant scheme that goes back to Born-Infeld. And I'll show you how this works. So this is the standard free particle Lagrangian, first year physics. And this is the relativistic particle Lagrangian, sort of done in year 2 or 3, say. And if you rewrite the relativistic Lagrangian by trying to force in the free particle Lagrangian, well, you throw in some factors of m, and then you identify the numerator as actually the free particle Lagrangian, and then you can simply identify the denominator as some kind of scale. You can rewrite the relativistic Lagrangian as the non-relativistic free particle Lagrangian in this very specific form with the square root onto lambda. And you can somehow refer to this as a Born-Infeld scheme. So take any Lagrangian L, introduce a new scale, and write this. And what you do is, in this particular setting, if you consider the limit when lambda goes to infinity, you actually get back the Lagrangian L. And if you make a Taylor expansion near lambda infinity, it starts with L plus or minus some corrections in L, which then are no longer invariant because they depend on the scale lambda. And I think this is probably the best way of thinking about this. So this is one way to break scales and be controlled about this. And if you do this in the teleparallel framework, so I just showed you the calculation, you end up with the torsion scalar, and then this term, a quadratic term that divides by lambda. And you can, for instance, show, so I did this with my colleague Franco Fiorini, you can actually show that in this framework, you can find regular black hole solutions in f of t gravity. And this goes back to results that were discovered previously, that you can replace the big bounce, the initial singularity in the universe by a bounce-like scenario with exactly the same approach. And as I said, so if you send lambda to infinity, this term, which breaks local Lorentz invariance, actually disappears. So somehow there's a certain scale at which Lorentz invariance is broken. And an interesting fact with this f of g model that I've talked to you about, so Milgram published something in 2019 where he actually was discussing a link between f of q gravity and this f of g gravity. And when you look at this carefully, you can actually think about the Mond parameter that is introduced in this model as the kind of new Born-Infeld type length scale. And Milgram did make two observations. And one was that the general relativistic limit is achieved when L goes to infinity. So this is sort of consistent with the way we are setting up this Born-Infeld scheme. And then he says that if you want to get the deep Mond limit in the limit where L becomes small, then your function f needs to have a specific form. So it needs a scale like x to the 3/2. And it turns out, so I had a quick look at this, you can actually use a Born-Infeld type scheme to achieve both these limits. And the only difference you have to make, so in the Born-Infeld scheme, you see there's a square root here. And if you want to reproduce Milgram's result, instead of a square root, you need a 3/2, which more or less gives you this 3/2. And then in the other limit, you get general relativity. And the interesting thing is that actually this particular function hasn't been studied yet. So if someone is interested in these kind of models, this would be an interesting function to study because it contains the deep Mond limit and the GR limit in a controlled way. And as I think I have 2 minutes left, so that's very good. So let me try to give you a bit of a brief summary of what I've tried to tell you. So there are too many modified theories of gravity out there. So I think most of you that have looked into this would agree, because if you just go onto the archive these days and look for modified gravity, it is literally thousands of papers. And many of these different theories can look really, really completely unrelated. And what I'm trying to do is I'm sort of trying to bring some order into this. If you look at these various modified theories of gravity and you include non-minimal couplings, you get actually so many possible combinations of models that basically you can spend all your life writing down different models. But that's not necessarily useful because you cannot make sensible predictions that have a physical meaning if you just do this. And what I'm sort of trying to do is I'm interested in creating a kind of more unified framework where one can study a very large plethora of these theories using a single approach. So instead of, as I said earlier, instead of studying one theory at a time and doing the same calculation over and over again for different settings, I'm interested in creating a framework that is sufficiently general, we can do the calculation once, and then it can be simply applied to all these different theories. And the results are stable in this propagation from the large theory to all the other sub-theories. And I would very much hope that eventually we are able to do this and to derive some fairly general constraints on modified theories of gravity that are applicable to a large array of theories. So not just to a very special theory, so to many other theories. And if you're interested, especially in our f of g and f of b framework, so recently published in Physical Review D with my PhD student, Eric. So it's quite a long paper. You can't read this in 5 minutes. It's almost 30 pages long. So take your time and have probably a strong coffee before you start. Because it's a bit long, and this is the reference to our 2015 paper. And I didn't include many other references. They're so easy to find. So thank you very much. And I think I managed to do well on time.